Today we're going to talk about ice tables, or initial change in equilibrium tables. These are tables that are used to solve equilibrium problems in chemistry. So, let's start with an example. This problem asks, 4 moles of HI are placed into a 5-liter flask and heated to 800 degrees. The system is then allowed to reach equilibrium. What will be the equilibrium concentrations of each species? So, we notice right off the bat that we have the equation for the reaction and we have the Kc, which means that we're going to be dealing with concentration for this problem. We should also notice right now that Kc is small. So for this example, we won't have to do the quadratic equation. Now we can go about filling in our table. Since the problem gives us the initial value of HI, we know that we're going from products to reactants in this reaction. So, we have 4 moles in a 5-liter flask, which means that the molarity is 0.8. We care about that because for concentration, we need to be using molarity rather than moles. So we can fill in 0.8 for our initial concentration of HI. Since they didn't provide us with any of the product concentrations, we automatically assume that those concentrations can be 0. So, now we can go back and remember from Chem 1 that when we're given a balanced equation, the coefficients of each element or molecule tell us the ratio in which those elements react with each other. So, for this equation, we can say that for every 2 moles of HI, we'll get 1 mole of H2 and 1 mole of I2, which is important for our ice table because we know that as 2 moles of this go, we'll get 1 of each of these. Since we're doing the forward reaction, we know that our change is going to be subtraction for our reactants and addition for our products. And since we don't know what exactly is going to happen and we don't know exactly how much we're going to get, we're going to denote the change with an x. And then our equilibrium, we'll just substitute in that x. So we will do down here 0.8 minus 2x, and then we'll just get x for both of our products. That's how you would go about filling in an ice table when you don't know the equilibrium concentrations at all. Now that we have our ice table filled in, we can go about solving the rest of the problem. What we'll do is we'll use our already known equilibrium equation. So we know that an equilibrium equation is the concentration of products over the concentration of reactants. So for this equation, that would look like this. Concentration of I2 times the concentration of H2 over the concentration of HI squared. And we're getting that squared from this coefficient. Now, our equilibrium concentrations can just be substituted in. X times x over 0.8 minus 2x squared. And we know that this and this are both equal to Kc, which is 16 times 10 to the negative 6th. Usually, if we were going to try and solve for x, we would have to use the quadratic equation. But since in this problem, Kc is so small, we can get rid of the x in our products, or in our reactants. So we'll just cross out that x, and it no longer matters. And the same for the 2. So I'm going to move this up so you can see it, but we'll just solve the bottom with the 8. Our equation becomes x squared over 0.8 squared equals 16 times 10 to the negative 6. And that's something we can solve. So I've put the solution for that up on the screen. Now we know that x is equal to 0.032. And we can put that information in to the equilibrium row of our ice table to find our concentrations, because we can solve this expression. So to do that, I'm just going to write HI, H2, and I2. Since in the equilibrium row, H2 and I2 were actually just equal to X, we know that their equilibrium concentrations were 0.0032 moles for, molarity. So it's actually molarity, because for ice tables, we use concentration, not moles. Make sure that that's something you're paying attention to, because it will catch you up. For HI, we have to actually substitute in X to our equation, which will be 0.8 minus 2 times 0.0032. And that will equal 0.7936 molarity. So we know that the answer to what will be the equilibrium concentrations of each species is this information. To sum it all up, we can fill in ice tables using concentrations and the coefficients of a balanced reaction, and that will help us solve for the equilibrium row. Then we can use the equilibrium equation and the Kc value to solve for x and find our equilibrium concentrations.